It's a great pleasure. It's my great pleasure to introduce Elisabeth Werner and her talk about convex floating bodies of equilibrium, based on joint work with Han Hank and Boaz Slomka. Oh, and Dan Florentine, Karsten Schund, and Ning Zhang. So, Elisabeth.
Thank you, and thank you very much for the invitation and the opportunity to talk. And you already gave the title and with whom I was collaborating on this. So let me right away go to what was at the origin of our work, namely Ulams Problem, which actually dates back to 1959. So it's an old problem. And what does Ulams Problem ask? Well, it asks if the Euclidean ball is the unique body of uniform density which floats in a liquid in any direction. And I'll explain in a second what's meant by floating in equilibrium in a given direction. But let's fix notation right away. So a body that's having this property, that is that it floats in equilibrium in any direction, we call such a body an Ulam floating body. And also right away, we'll always assume, and we can do that without loss of generality, that the density of the liquid is equal to 1. So what does it mean now that a body floats in equilibrium in a direction u? Well, it means the following. So let's look at a picture. So we'll have here a body K, say, that floats in water. So the water surface is given by this hyperplane HU, that is the hyperplane like so, drawn here, which has outer normal U. So that's describing to us the water surface. Then this hyperplane splits the space in what is above the water surface, namely the half space HU plus, and the half space that's below the water surface, HU minus, I'll denote it. And then we'll also need G, which is G of K, the center of gravity of K. And by B plus, we'll denote the center of gravity of the part of K that is above the water surface. And by B minus, we denote the center of gravity of the part of the body that is below the water surface. Then, and that's the definition, U is an equilibrium direction for K, or K floats in equilibrium in direction U, if G minus B, so this vector here, G minus B, is parallel to U. So in our picture, it looks like G minus B minus, being this vector, doesn't look like to be parallel to U. So in that example, K doesn't float in equilibrium in direction U. Okay, so if U is an equilibrium direction for K, then this is the definition, but then it's easy to see that that is also equivalent to G minus B plus is parallel to U, and B plus minus B minus is parallel to U. Also, what is easy to see is that if U is an equilibrium direction for K with relative density rho, then minus U is an equilibrium direction for K with density 1 minus rho. Just, you know, in the first part, we'll look at things like so from above, and in the other part, we would reverse direction and look at things from like below. So we have this symmetry about rho and 1 minus rho. That's why it's enough to consider the relative density to be smaller or equal than 1/2. Good. Now, what I want to do first is give you some background on what is known concerning Ulams problem, and then give you one result of ours. So, what is known about Ulams problem? Well, it was relatively early, seen after Ulams problem was stated, that there are actually counterexamples in dimension 2 with relative density rho equals 1/2. So there are other, it's not just, well, in dimension 2, it's not just the Euclidean ball that floats in equilibrium in every direction. And these counterexamples are what we call, they were given by Auerbach, so we call them the Auerbach figures. So let's show how the Auerbach figures look like. Okay, so we'll give parametric equations for the boundary of the Auerbach figures. I'll denote the Auerbach figures by AK because it depends on a parameter K. K bigger or equal than 0. And so the parametric equations for the boundary are given as follows. So theta runs between 0 and 2 pi. And I'll abbreviate, we also will have a function f, which is simply minus k cos 3 theta. So I'll abbreviate it by f to make things a bit shorter. So then what are the parametric equations of this Auerbach figure AK? Well, the x-coordinate of a boundary point, x ak of theta, is given as so. So it's minus sine theta f of theta plus f prime of theta minus 1 cos theta. And the y-coordinate of a boundary point is similarly given by this equation here. Now notice that if k is equal to 0, in which case the function f is 0 and consequently f prime is 0, we'll just get that the x-coordinate is minus cos theta and the y-coordinate is minus sine theta. So if k is equal to 0, then the Auerbach figure is a ball, but that's actually the only case when the Auerbach figure is a ball, only if k is equal to 0. Now, I have drawn some pictures of Auerbach figures, and we can see that they can both be convex or non-convex, like this blue one, which corresponds to, if I remember correctly, to something like k equals 0.1. Then we'll get an Auerbach figure that is non-convex, but floats in equilibrium in every direction. And if we look at the red one, which corresponds to k equals 0.02, then we'll actually get convex Auerbach figures. So there are counterexamples in dimension 2 with relative density rho 1/2. There are also counterexamples in dimension 2 with a relative density different from 1/2, and those are due to Wegener. These are not symmetric, which will be important in our context. And also there are counterexamples in higher dimensions by Wegener, but some of them are not even convex and holes are allowed.
Sorry. And do I understand this properly, that if you put those triangle-like figures in water, in any angle, so they will float and will not rotate?
Oh, well, it's not so that the thing is supposed to be staying static. We'll actually, move the thing around because we will really look at every possible position. We don't want this thing to stay static.
Okay.
Or if you want, you can move the water surface around.
No, I mean that, imagine that I have made this figure that from the previous slide, this two-dimensional figure, and I fixed it and put it in the two-dimensional water. So if I let it go, it will not rotate. If I put this...
That's right. So that's what I mean. If you put it in there, it will not rotate.
Great. That's nice.
Okay. Yeah. So did I answer your question?
Yeah.
Okay. Clear? I can go on?
Yes, please.
Okay. So that's a little bit of a background, what is known concerning Ulams problem. And there are more partial results, positive and negative, concerning various densities. But by and large, Ulams problem, and mostly so also in higher dimensions, remains open. So what I want to discuss today is a positive answer to Ulams problem in the case of where we restricted ourselves to the class of symmetric convex bodies with relative density 1/2, and there, we found a positive answer, and that is our first theorem, the Theorem 1, that is joined with Dan Florentin, Carsten Schütt, and Ning Zhang. So what does it say? If we look at a convex body K in Rn that is symmetric and has volume 1, having volume 1 is not important, it's just a normalization and makes things occasionally write down a little bit shorter. So this volume normalization is not important, but symmetry is important. So symmetric convex body of volume 1 and density 1/2. Density 1/2 is also important. Then K is an Ulam floating body if and only if K is a ball. Well, if K is a ball, then of course it is an Ulam floating body. So the only interesting direction is really the direction from left to right. So the problem has a positive solution if we restrict ourselves in any dimension to symmetric convex bodies of relative density 1/2. And in dimension 3, this was proved by Faulkner and Schneider. So I will try to give an idea of the proof of the theorem. So to do that, I need to provide all the tools that we need in order to give such a proof. So let's start by providing the tools to prove the theorem. So one of the tools that we need is the convex floating body, which I'll denote like so, K delta, that was introduced independently by Barani and Lahmann and by Carsten Schütt and myself. So how is it defined? Well, we'll give ourselves a parameter delta bigger or equal than 0 and not too large, so that the thing that we obtain in the end is not the empty set. Then K delta is the intersection of all half spaces H delta U minus, whose defining hyperplanes H delta U cut off a set of volume delta times volume K of the body K. So by these two parallel bars, I always denote the volume of the body or whatever set we look at in its dimension. So picture is as follows. Here we have a convex body K. We look at hyperplanes H delta U. Well, eventually, the U is not important now. Eventually, if I write it like so, U will be an outer normal to the hyperplane. So we look at such a hyperplane H delta U that cuts off a set of volume delta K, volume K of the body. Then this hyperplane gives us two half spaces, H delta U minus here, and the other one H delta U plus. And we intersect all these half spaces, H delta U minus, and do that for every hyperplane H delta that cuts off a set of delta times volume K from the body. And then we'll obtain a convex body, of course convex, because we look at the intersection of half spaces, and half spaces are convex. So we'll get a convex body, which we call the floating body, that sits in K. So obviously, K delta is convex. I'll mention some other properties, but only those that we will be needing in order to prove the theorem. This floating body has many other very nice properties, but let's only mention the ones that we need that we need today. So one thing that was observed by Carsten and myself is that there is a delta 0 positive, such that K delta 0 reduces to a point. And in fact, if K is symmetric, then this delta 0 can be chosen or is equal to 1/2, and the point to which K delta or K 1/2 reduces is the center of symmetry. If K is not symmetric, then it can happen that this delta 0 at which stage the floating body reduces to a point is strictly smaller than 1/2. And an example is the simplex in Rn, or the triangle in the plane. Okay, so that's one thing that we'll need. Now, the other thing that we'll need is another concept of floating body, which I can be called the Dupin floating body. I'll denote it like so, K with these square brackets delta. And that was introduced by Dupin in dimension 2 and 3, but of course it goes in a similar way in higher dimensions. So what is the Dupin floating body? It is this set contained in K whose boundary is given by the centroids G. What's G? It's G of K intersected H, where H is a hyperplane that cuts off a set of volume delta times volume K from K. So here is the picture. Here we have our convex body K. We look at a hyperplane H and intersect it with K. Then we look at the intersection K inter H. And G is the center of gravity of this intersection. And we'll trace out all these centers of gravities for all possible hyperplanes that cut off delta from K or delta volume K from K. And tracing out these centers of gravity, we'll get this Dupin floating body. Now,
excuse me.
There's a problem. Yes.
Yeah, you answered my question in the next slide. Yeah. Sorry.
So there is a problem with this Dupin floating body. Namely, it need not be convex. So we leave the class of bodies we are. Actually, we only are interested in, namely, the class of convex bodies. And to see that it is not necessarily convex, we'll take a triangle in the plane, let's say of volume 1, then I don't have always to say it cuts off delta times volume of the set. So let's say triangle has volume 1. So what do we get if we trace out the centers of gravities of hyperplanes H that cut off delta? So let's start with a hyperplane that's parallel to one of the sides, the red one that I have drawn here. And then the center of gravity of this H inter the triangle is just this red dot here. Then as the hyperplane moves up here and down here, all the while cutting off delta, our center of gravity moves along this curve here till we hit or till our hyperplane goes through this vortex here, all the while cutting off delta. Then as we move away from this vortex with the hyperplane and towards the other vortex up here, our center of gravity will move along that curve here till we have reached this lowest point of that curve, which happens to happen when we look at the hyperplane that cuts off delta and is parallel to this side here, and then we'll keep moving up here and so on. So that's what we get if we look at Dupin's floating body, and as I said, we get something that we don't want because it's not convex. By the way, the convex floating body, that is the intersection of all the half spaces of hyperplanes that cut off delta, is simply that object here where, so to speak, these fishtails have been removed. So one can now look at the question when actually this Dupin floating body coincides with the floating body. And actually it happens that if the Dupin floating body is convex, the two coincide. And the fact, one instance when this happens, that the Dupin floating body is convex, that is when the two coincide, there is, was shown by Meyer and Reisner. They showed that if K is symmetric, then the Dupin floating body and the floating body coincide. So in particular, K delta, the Dupin floating body is convex. Okay, so that's the other tool that we need. And what else? We also will need the relation between the relative density rho and the cut-off volume delta, or delta times volume K. And again, I repeat that without loss of generality, we assumed always that the liquid has density, so rho L, density of the liquid is 1. And also, most of the time, I'll assume that the body K has volume 1. and that is without loss of generality. Then by the Archimedean law, we know that the weight of K, supposedly the body swims, right, and doesn't sink plop completely under. So if the body swims, then the weight of K is equal to the weight of the displaced water. So the weight of K is equal to rho times the volume of K times the gravitational constant. Volume of K is 1, so we'll just get rho times the gravitational constant, which I have right away omitted because gravitational constant would also appear on the other side, so it cancels out. So we'll get that rho is equal to, now comes weight of the displaced water, which is the density of the liquid, which is 1, times the volume of the displaced water, but the volume of the displaced water is the volume that the body takes away under the water surface, and as we assume that the volume of the body is 1, so this is just 1 minus delta. So we'll get that the relation between the cut-off volume delta and the relative density is rho is equal to 1 minus delta, and we'll need that. We also need what Han Huang and Boas Slomka called the metronoid, and denoted by m delta k. So how did they define this? Actually, the metronoid is this body whose boundary consists of the centroids of those parts of those parts of K that are outside or above the water surface. So let's look at a picture. So here is body K. We look at a hyperplane H delta U that has outer normal U, and that cuts off delta from delta volume K from the body K. So this yellow set here has volume delta times volume K. Now, before, what we had been looking at is the center of gravity of H delta U intersected with K. That is, before we had been looking at this, what I now denoted by YU, in the context of the Dupin floating body. And we saw that this doesn't give us necessarily a good object. What we look at now is the center of gravity, and we'll denote it by xk delta of U, of this yellow part, that is the part that sticks out of the water. And then it was shown by, and we'll do that for all such hyperplanes, and then we'll also get traced out a set whose boundary points are given as the center of gravity of that construction here, and was actually what was shown by Han Huang and Boas Slomka. Not only is the body that one gets convex, it's actually strictly convex. And of course, there is a relation with the floating body. Obviously, the metronoid does contain the floating body with index delta, but actually one can do a little bit better. Namely, it contains the floating body with index E minus 1 over E times delta, and it's contained in the floating body with index delta over E. Okay, so that's this metronoid. And if we think back for a second, when we talked about Ulams problem, also these centers of gravity of these parts that are outside the water surface that we then call B+, they were also playing a role. So it's natural to assume that there is a relation between the metronoid and the Ulam and an Ulam body. So let's see what's this relation. And that was an observation done by Han and Boas and myself. So we noticed that actually K is an Ulam floating body if and only if, so delta is fixed sufficiently, delta is fixed. So K is an Ulam floating body if and only if the metronoid with index delta is a ball. And that was actually crucial. This observation was crucial to us in another a tool that we need to prove our Theorem I. And what we also need to prove our Theorem I is another observation by Han, Boas, and myself, which goes as follows. So suppose we have a convex body in Rn without loss of generality, it has volume 1, and also without loss of generality, its center of gravity is 0. Then the metronoid with index 1 minus delta is equal to the metronoid with index delta multiplied by minus delta over 1 minus delta. And the way we'll actually use it more precisely in the proof of our theorem 1 is in the case when delta is equal to 1/2. So this proposition is not too hard to prove, but we'll need it only for the case delta is equal to 1/2. What happens then is that on the left-hand side, we'll get the metronoid with index 1/2. On the right-hand side, we'll also get the metronoid with index 1/2, but now multiplied by -1. So that shows us that with index 1/2, that is the metronoid m1/2 is symmetric. Okay, now comes our last tool to prove our theorem 1, and that is theorem 2. And that is, this theorem 2 is actually the crucial ingredient for the proof of theorem 1. So what does it say? So it's a bit technical, and the proof is also quite technical, so I cannot show it. So let me try to explain a little bit what it says. So we'll have a delta in 0, 1, 1/2. Delta equals 0, by the way, is completely, if delta is equal to 0, then the floating body will just be the body itself, so that's not interesting. So we'll take delta in the interval 0, 1/2, and K is a convex body such that the floating body K delta is C1 or reduces to a point. Then K is an Ulam floating body. If an Ulam floating body, remember what is an Ulam floating body? Was a body that floats in equilibrium in every direction. So K is an Ulam floating body if and only if there exists an R bigger than 0, such that this condition here holds. Now, if we look at this condition, then on the right-hand side, we'll have a constant, and on the left-hand side, we'll have this expression here, where we integrate what? We integrate for all u in Sn minus 1, and for all v in u perp, the subspace orthogonal to u, and all such v that they also have norm 1. So for all such u and v, we integrate the inner product of x with v squared, where what the x are taken out of k intersected with a hyperplane that's orthogonal to u and cuts off a set of volume delta from k. So we integrate these second moments, and what do? We subtract here the center of gravity of this hyperplane section, also hit with v squared. And this expression then is supposed to be a constant, and that happens if and only if K is an Ulam floating body. Now, this condition here basically is a kind of isotropicity condition. If you think what it means that a convex body is in isotropic position, so what we usually assume is, or what the definition is, actually is that the body has volume 1, well, that's not the case here, and that the center of gravity of the body is at 0, then such integrals now over the body K are second moments of such integrals over the body K now are equal to a constant. So it's natural when I say that this is a kind of isotropicity condition that we have here, that we have also to do a positioning of the body, which is usually done if one formulates that a convex body is in isotropic position. One positions the body so that the center of gravity is at 0. So it's not surprising that we also, as we want to interpret this as an isotropicity condition, that we have to always subtract the relevant center of gravity to get the right positioning. That's why this term here comes in. So that was to explain a little bit why this term comes in. So, and then what happens is that in that case, that is, if this condition here holds, which is equivalent to k be an Ulam floating body, then in that case, the metronoid is a ball of radius r. And actually what we'll do to prove this theorem, we show that this condition is equivalent to the corresponding metronoid being a ball of radius r, and then that tells us by the observation of the previous slide, this is actually equivalent, that the body is a Ulam floating body. So we'll actually go through, to prove this theorem, we go through, together with this previous observation, through showing that it is, in that case, a metronoid. Now, we have
Elisabeth,
here two, yeah?
May I ask a question?
Sure.
Yeah, and here we can write that it's an inner product x minus centroid with v squared, yes, because the linear part disappears.
Right. Mm-hmm.
Yes, but then it's the same, actually, that condition. Then if you rotate slightly a body in any direction, I mean perpendicular to the U, then somehow, how to say, that our body in the first order swept out the same volume.
What has the same volume?
I mean, you have your body, yeah,
Mm-hmm.
probably this. Yes, k delta, and then you choose one vector U and start to rotate your body with respect to in direction U plus v, probably U plus tv. I mean for small t,
Mm-hmm.
and then in the first order, I see I don't know, but I have encountered in such in a similar condition. That means that actually in the volumetric speaking, that if you rotate, that you lose some parts and add some parts, yes, to your volume. You might consider it in such way.
Mm-hmm.
And I think that it's exactly the form that your condition, that geometrically speaking, it doesn't matter in what direction you will rotate, you will have always the same, how to say, volume difference or whatever. I mean,
yes.
It's better to draw a picture.
Yes, I think you are right.
I mean, but have you any like geometric intuition behind this, except of this isotropic position?
Not really. Maybe it helps a little bit if we go to see, because here we have actually two assumptions. The one is that k delta is C1.
Yeah.
And that is actually giving us, so why do we need this? This is actually giving us that, so if k delta is equal to C1, we can actually show that the floating body is equal to the Dupin floating body, which gives us then this nice characterization of every point on the boundary being the center of gravity of a hyperplane that cuts off delta, which, would then go in this direction that you were saying. I think you were trying to say that happens if you rotate, then you'll add a little bit and you'll subtract a little bit, you'll add a little bit on one side, subtract a little bit on the other side. But yeah, so that would kind of, go in the direction what you were saying. So that was what this C1 does for us. Then the other thing is that the floating body reduces to a point which we can assume to be 0, and then in that case the condition reduces simply to this condition here. So then we do not need to consider the center of gravity. We do not need to subtract this anymore. Does that help?
Yes.
Okay. So maybe I go on. Okay, I will say a little bit more about that anyhow in a moment. So let's go on, and let's now start with the proof of theorem 1. So I have repeated the proof. I have repeated the statement of theorem 1. So we take K convex body that's symmetric, and actually now I assume without loss of generality that the center of symmetry is at 0 of volume 1 and of relative density 1/2. We have to show that if K is an Ulam floating body, then K is a ball. So let's start with the proof, and we'll put in all the ingredients that we'll have. Like K has volume 1. Which we can do without loss of generality, and rho, the relative density, is 1/2. We have established the relation between rho and the relative density rho and the cut-off volume, which is now just delta, which was this one, which shows us that delta is equal to 1/2. We know that K is symmetric or zero symmetric and delta is 1/2. Then K 1/2, that is the floating body, reduces to a point which is just the center of symmetry, and in this case it's then just 0 because that's the center of symmetry. Because for symmetric bodies the delta for which it reduces to a point is 1/2. Now we want to use the theorem, this theorem 2. As the floating body reduces to a point, we know K is an Ulam floating body if and only if this condition, this simplified condition where we now need not subtract the center of gravity, is a constant, and that happens for all u in Sn-1 and for all v in u prop that have norm 1. So now what we want to do is we want to rewrite this condition here. And basically it's simple. What we want to do is we want to use polar coordinates on this condition. So to do that, we will also need the radial function of a convex body, which for a direction psi in Sn-1 is defined as follows. So Rk, the radial function of k in direction psi, is the maximum over lambda bigger or equal than 0 such that lambda psi is in k. So you have the direction psi, and then you'll take this lambda, how far you have to march in direction psi till you leave k. So let's now look at this condition here and let's rewrite it. So we'll fix u in Sn-1 and take v of norm 1 in u perp, and our condition is this one. Now we know that the floating body has reduced to a point which we can assume to be 0. So what we look here is at a hyperplane that cuts off actually delta is 1/2. We look at a hyperplane that cuts off 1/2 and is orthogonal to u, and that's a hyperplane that is a support hyperplane to the floating body, which is just 0. So this is actually just a hyperplane going through 0. So it is what we look at here is u perp inter k. So in u perp inter k, we now look at polar coordinates. That is, we write x equals t times psi. We use polar coordinates in u perp inter k, which gives us u perp inter Sn-1. Then we also want to stay in k. So if we have a direction psi given, we want to stay in k, so we should only march as far out in direction psi till we are still in k. So we'll go up to the radial function of k in direction psi, and then we'll get t to the n psi inner product v squared dt d sigma of psi, where sigma is just the usual surface area measure on Sn-1. Now we'll integrate with respect to t and simply get 1 over n plus 1, this integral over u perp inter Sn-1. If we integrate the radial function raised to the power n plus 1, and we'll have this inner product psi v squared still there. Now what we want to do is we want to average over v. So to do that, we'll look at the normalized Haar measure on Sn-1 and Sn-2, which is the Sn-2 is just where we take out the v, so it is Sn-1 inter u perp. So that's the Sn-1 that we look at, and then we observe that for all x different from 0, the integral of these second moments, where we integrate over Sn minus 2, now with respect to the normalized Haar measure, is just 2 times the n minus 2-dimensional volume of the n minus 2-dimensional Euclidean unit ball divided by the n minus 2-dimensional volume of the n minus 2-dimensional sphere times the Euclidean norm of x. And that's actually also not too hard to show. So that's what we do now. We average over all D. That is what we'll do, kind of. So what we'll do is we multiply both sides of our identity that we have up here with, so to speak, 1. So mu is the normalized Haar measure on Sn minus 2, which is Sn minus 1 into U perp. So what we have here is 1. We multiply C with this 1. And also on the right-hand side, we multiply with this 1, which is this integral over d mu. And then right away, we have pulled the sigma integral under the mu integral. So I've written this again. We've pulled the sigma integral under the mu integral. And now we change integration. We'll integrate first with respect to mu and then with respect to sigma. Now integrating with respect to mu gives us the exact expression that we had on the previous slide. So in comes the expression that we saw on the previous slide, 2 times this volume of the ball divided by the volume of the sphere. And it remains this integral over the radial function raised to the power n plus 1. Or now we are rewriting this expression. We bring the Sn minus 2 volume to the one side. Sn minus 2 volume, that was just sigma of, in our situation, Sn minus 1 into U perp. So it's just this expression here that is equal to, we'll look at the right-hand side where we have also divided by C, and recall that this was just 1. So that gives us the right-hand side. And then we'll subtract on both sides this integral or the sigma over Sn minus 1 into mu perp. And what we'll get is 0 is equal to this expression here. So the integral over Sn minus 1 into U perp of the radial function raised to the power n plus 1 times this constant that depends only on the dimension. So let's call it little cn minus 1. Okay, so I've written it again. So 0 is equal to that expression here. And now we recognize that this expression that we have here on the right-hand side is nothing else but the spherical Radon transform of this constant Cn times radial function to the n plus 1 minus 1, because for a Borel function on Sn minus 1, the spherical Radon transform, this calligraphic R of a function f is just evaluated at a point u, is just this function that is defined exactly like so. It's the integral of f over Sn minus 1 into U perp. So we'll have the radial function of our function, the spherical Radon transform of our radial function up here. And now there is a theorem about Radon transform that says that if f is a bounded even Borel function on Sn minus 1, such that for all u in Sn minus 1, the Radon transform of f, which is this expression here, is equal to 0, then f is 0 sigma almost everywhere. So in our situation, we have actually that the radial function of k is even because k is symmetric convex body. So, and of course the radial function of k is bounded because k is a bounded convex body. So by this and the theorem, we'll get that R of k, the radial function, is constant for sigma almost all u. And as Rk is continuous, we'll get that actually Rk is constant for all u, and therefore k is a ball. And so this proves the theorem 1. Okay, and I'm finished, and I'm sorry I went a little bit over time. So thank you very much.
Was perfect. Thank you. And but in theorem you have only the statement when you fix the density. Yes.
Yes, the density is fixed at rho equals 1/2. So
1/2.
Yes. So
and,
it is. Yeah.
What do you think about like other densities? Or can you use the same method?
We thought a little. It's been a while that we have looked at the problem, and because it was it was while Dan Florentin was still at Kent State, and then he in the meantime has moved back to Israel, so he had to get resettled back home, so to speak, and also Ning moved back to China, so he had to get resettled back home there. So we have not looked at things for a couple of months now, but I remember at some point we did look a little bit at different densities, but couldn't, make any progress, at least then. And I'm sure we'll get back to the problem once everybody is, so to speak, installed back home. And once, we can actually, well, it's nice to communicate via Zoom, but it's even nicer to communicate when it's actually communicating in person.
Yeah, no doubt. And I have another question, probably not directly connected with your talk, but are you aware of any relation between this delta floating body and Santalo inequality? For example, there is, I can elaborate a bit, there is a Santalo inequality due to Mayer and Pajor, I guess, that they were the first one, when they said that, okay, we have a hyperplane that cut off the part of a convex body, yes, lambda part, let's say, then we can write a Santalo inequality with respect to, and where we consider the duality with respect to the sum point in this hyperplane. Yes, and but the coefficients on the right-hand side would be something like Q4 over lambda times 1 minus lambda.
Yeah, exactly. It's like a bit of a strengthening, right?
Yes, yeah, it's my displacement. Yes. And here, can you say, so I just, for me, it's a natural question. Can you say something like this about the points on the boundary of your delta floating body, at least in symmetric case? So, for example, in the Meyer-Pajor result, there is a point somewhere in this, yes, in this hyperplane. And what if we choose all these points? So what will happen?
Actually, in the context of the floating body, I'm not sure. I have not thought about this, but actually with Mathieu Meyer, we looked at something at some point, which then led us to define bodies that are, so to speak, related to the Plaschke-Santalo inequality, and those bodies we had called, Mathieu Meyer and myself, we had called Santalo bodies, and they are closely related to the floating bodies. So it's been a long time ago, so let me think how the construction went. So you have a convex body K, and what we looked at, so you can establish duality, that is, you can say, okay, volume K times volume of K polar taken with respect to a point Z. So this is smaller or equal than volume of the Euclidean ball squared, if you choose the point Z to be the Santalo point, right? Now, what we did with, and of course, you can't march too much away from the Santalo point, because then the product may explode, right? If you would march towards with a point with respect to which you do the polar, if you would march towards the boundary of the body, then your volume or polar volume becomes infinite. But what we did with Mathieu, and I don't remember where we put the parameter, so we looked at volume K, and then we took volume K polar with respect to a point Z, and that was not supposed to be smaller or equal than volume of the Euclidean ball squared, but smaller or equal than, say, T times volume of the Euclidean ball squared, and T was a parameter allowed to run, and or to be bigger than 1. Then we looked at all those points Z in the body for which this Blaschke-Santalo inequality holds with this parameter T, and that gave us a convex body in K, which has many properties similar to the floating body. So
yeah, I mean that was my question actually.
Because, okay, perfect.
I mean, it's clear that it's somehow related, because when you cut off some parts of the body, even if you prove this Blaschke-Santalo, this Merpajor version of Blaschke-Santalo inequality, then actually you project like along this centroid, yes.
Mm-hmm.
And so I thought that perhaps for some bodies, these delta floated bodies are exactly the set that you will get. So, but you don't know such a result.
No. What I know is what I just told you about this, what we had called Santalo bodies, I believe. Yeah. So there are 2 papers with Mathieu Meyer and myself where we looked at that. Yeah. Okay. And actually, that might be interesting to you. I seem to remember also that we related it also to the ellipsoid of maximum volume inside the body.
Okay, thank you.
Yeah, which shows me maybe it would be nice to look at. It's good that you asked this question. Maybe it would be interesting to look at a functional version of those things. Yeah.
Yes. At least for me, it's very interesting.
Yeah. So.
Okay, thank you. It was very nice talk.
Thank you. Thanks.
Thank you very much.
I think it's all for today.
Yeah. So see you tomorrow.
See you tomorrow.